So in the last lecture for the circuits chapter, we're going to look at what happens when we put resistors and capacitors together in circuits. So just a quick review of what was in the main lecture. When we hook up a resistor and capacitor in series to a battery, charges flow from the battery onto the capacitor, and as the capacitor charges up and the charge increases, the voltage on the capacitor also increases. So what happens is that the current flows very quickly initially, but as the charge on the capacitor gets larger, it starts to repel the current that's coming onto it, and so the current gets slower and slower and slower. So what happens is that the voltage on the capacitor and the charge on the capacitor increase with time, and the current decreases exponentially with time. The voltage and the charge start at 0 and they go up and they asymptotically approach a maximum value of the battery voltage, or EMF E for the voltage, or Q max for the capacitor charge, and the current goes from its maximum initial value down to 0 in an exponential decay. The time constant for the exponential decay is given by the product of the resistance times the capacitance. The bigger that number is, the longer it takes for the capacitor to charge up. And we use the symbol Greek letter tau for the time constant, RC in seconds, and to calculate it we need to make sure we put the resistance in ohms and the capacitance in farads. Once the capacitor is completely charged, we take the voltage out of the circuit and we just hook up the battery so that it can completely discharge. What's going to happen is that the voltage, the charge, and the current are all going to decay exponentially with time, and they're going to have the same time constant tau equals RC as they did for charging. So when you're discharging, all of them start at a maximum and go down to 0. When you're charging, the charge and the voltage start at 0 at t equals 0. The current starts at its maximum value, which is the battery voltage divided by the resistance. And when you go to t equals infinity, the voltage on the capacitor becomes equal to the voltage on the battery. The charge then becomes its maximum value, which is C times the voltage on the battery, and the current goes to 0. So we just need to remember those and be able to do math with them. So let's start off with a simple calculation, which is just going to be primarily plug and chug. So here we've got an uncharged RC circuit. We're going to close a switch, and they tell us that we've got a resistance of 150 ohms, a capacitance of 23 microfarads, and a battery voltage of 6 volts. So let's just go through this step by step and figure out what's the time constant for the circuit. So time constant, that's my tau. It's just the R times the C. So R is 150 ohms. The C is 23 microfarads. I need to make sure I put that into farads. So 23 times 10 to the minus 6. Excuse me. And I get 0.00345 or 3.45 times 10 to the minus 3 seconds or 3.45 milliseconds. Okay, so that's how long the time constant is. What's the maximum charge? Well, the maximum charge on the circuit, that equation is given at the bottom. It's just equal to the capacitance times whatever the voltage is on the battery. So Q max, or Q0, depending which textbook you look at, is C times the battery voltage. So that's going to be 23. And again, I've got to put this into farads. So 23 times 10 to the minus 6 farads times 6 volts. And I get 138 times 10 to the minus 6 coulombs, or 138 microcoulombs. Okay, what's the charge then at 4.2 milliseconds? So look at the two equations below. Which equation is for charging and which one is for discharging? Remember, the charge starts off at t equals 0. Remember, e to the 0 is just 1. So at t equals 0, this one is 0. So this is the equation for charging, the one in the middle. And the equation for discharging is going to be the one on the end. So if I'm charging, I want to use this first equation, Q equals Q0 times 1 minus e to the negative t over the time constant. Okay, so I know my t is 4.2 milliseconds, my time constant is 3.45, and my Q0 is 138 microcoulombs. So I can just put in all the numbers that I have. I just have to make sure I put it into my calculator properly. E to the negative 4.2 milliseconds divided by 3.45 milliseconds. And because I have these both in milliseconds, I just left it like that, but you could equivalently put 0.0042 divided by 0.00345. You get the same answer. So if I put that in to my calculator, I get 41 times 10 to the minus 6 coulombs, or 41 microcoulombs. Okay, so now we say after it's been charging for a long time, then we take the battery out of the circuit and we let it discharge. So we're going to restart our clock when we disconnect the battery. We want to know what's the charge after it's been discharging for 4.2 milliseconds. So now I need to use the third equation. The third equation is the one for discharging. So now Q is equal to Q0. We know what that is. We've let it charge for a long time, so it's come up to its maximum value. And we've got Q0 e to the negative t over RC. RC is our time constant. We figured that out, and we figured out what Q0 is. So just plug in our numbers. 138 times 10 to the minus 6 times e to the negative t, 4.2 milliseconds, over the time constant, 3.45 milliseconds. And I get, oops, I read my numbers wrong, sorry. Hang on a second. So this one is 41 microcoulombs. So if you were wondering, if you put that in your calculator, you didn't get the same number as me, the answer for B, so for C, I was looking at my numbers cross-eyed, is actually 97 microcoulombs. So 97 times 10 to the minus 6, or 97 microcoulombs. Okay, sorry about that. All right, so that's simple plug and chug. You might be asked to do it for current. You might be asked to do it for voltage, charging, discharging. First thing you should always do is figure out what's the time constant for the circuit. Make sure you put the resistance into ohms. It might be given to you in megohms or kiloohms. And put your capacitance into farads. Again, it could be micro or nano. The more complicated one is where we have to do one where we have to pull something out of the exponential. So let's look at one like that. So here I've got a camera flash. It's got a 1200 microfarad capacitor. All right, so C is equal to 1200 times 10 to the minus 6 farads. And they tell us that in 95 seconds, so at t equals 95 seconds, the flash charges to 90% of its maximum charge. So what it tells us that Q for t equals 95 seconds is equal to 90% of its maximum charge. So it's going to be 0.9 times Q0. And what it's asking me is, what is the time constant and what's R? Okay, so I know C and I know T, and I know that at the time of 95 seconds, Q is equal to 0.9 times Q0. So how on earth am I going to find those other things? Well, first of all, let's look at what's my equation. So this is charging. So for charging, Q is equal to Q0 times 1 minus e to the negative t over the time constant. Okay, so what do I know? Well, I know my t, and I know that q is 0.9 times q0. So 0.9 times q0 is equal to q0 times 1 minus e to the negative t over tau. All right, so I want to try to get that tau out of there. And in fact, let me put in, I know that this is, my t is 95. So I'm going to say minus 95 over tau. So first thing I'm going to do is let's divide both sides by q0. All right, so then what I get is 0.9 is equal to 1 minus e to the negative 95 over tau. So I want to try and get that tau out of the exponential. So how do I do it? Well, first of all, I want to get the exponential on one side all by itself. So let me take it, I'm going to add it over to that side, and then I'm going to subtract the 0.9. Right, so what I'm going to get is e to the minus 95 over tau is equal to 1 minus 0.9. Okay, so e to the minus 95 over tau is equal to 1 minus 0.9, which is 0.1. All right, so I'm almost there. So now I need to get that tau out of the argument. How do I get the tau out of the argument? Well, what I need to do is I need to find the inverse function for the exponential. The inverse function for the exponential is the natural log. So what I need to do is I need to take the natural log of both sides. So I take natural log of the exponential. So natural log of e to the x is just x. So I'm going to get minus 95 over tau. And then on the other side, I'm going to have natural log of 0.1. Okay, so now I want to find the time constant. So the time constant, tau, if I rearrange that, tau is equal to minus 95 over the natural log of 0.1. And I get 41.26 seconds. Okay, so my time constant is 41.26 seconds. All right, so I've got that. How do I find r? Well, I know by definition the time constant is equal to r times c. So now I know my time constant, I know my c. R is equal to tau over c. So tau is 41.26. C is 1200 times 10 to the minus 6. It's important that you put that in there to get the right answer. And I get a resistance of 34,382 ohms, or 34 kilo ohms. Okay, so you need to be able to do this rearrangement and taking the log, natural log, to get it out. Probably not for a test, but definitely for the homework. You need to be able to do calculations like this. Okay, so what do I want you to do for your active learning problem? Well, I've given you here a circuit. It's got an R and a C given and a 12-volt battery. I want you to find the time constant. I want you to find the V, Q, and I at t equals 0 seconds. So what's the initial voltage, charge, and current? And then what's the voltage, charge, and current 6.5 seconds after you close the switch?